That is it. Today I'm going to start with a little bit of organization issues before we continue with the examples, what you have to configure, etc., so that I'm sure that you are following all the situation. So first of all, question I sent yesterday, I think yesterday, the results of the questionnaires of the first reading. Did you receive them? Okay, so for those that I'm not sure if you really check your lab in the account that you used in order to answer the question. So I don't know if you used your lab email address or another alternative, but it's in the one that you have used to answer the questionnaire, and of course have a look at the spam because it might go to spam, particularly if you use the lab account. It might land there. So with regards to the reading, sorry, sorry, this is my Siri intervening in my in my talk. Regarding the questionnaire and the readings in general, I have comments on the format, and then we will go very quickly through the questions to make sure that well, I'm not going to go through the questions together. What I will do is I will send a version with all the responses, the correct responses, so that you can compare and check, so that we do not lose time, like going through the questionnaire. But I have some format questions. When you use sentences or ideas from others, you have to cite the source. In many cases, of course, because we were kind of having a reading control, some of you more or less copied pieces of the sentences in the articles that you read. When you do that, you need to cite, if it's the exact sentence used by another person, you have to put it in quotations, and you have to cite. And since these are very particular documents, you have to cite with the reference of the article, and then the page and paragraph that where you found them and you copied the site. Okay, this is very important because this is a main difference of going to the university, that this type of practice you are aware of and you use it. Okay, so for the next readings and the next everything in your life, when you cite someone, if it's a direct citation, then you put the citation in quotes and you give the reference, the bibliographical reference. And if this is the ideas, but you are using your words, then you just cite the reference without putting into quotes, because these are your own words. So that is something that it's important to do, otherwise you are committing plagiarism. And even if you use a document from yourself, this is auto-plagiarism that exists. So you always, when something comes from a specific source, you have to declare the source. So that's one thing. The other thing that I observed, of course, we are all, well, I don't know if we have here a native English-speaking person. I'm not a native-speaking person, and some of you aren't neither. So anyway, even if we are, if this is the case, you need to respect the grammatical rules as much as possible. For example, you begin your sentences with capital letters. You, in general, do not use capitals within the sentence, and you end sentences by a dot. And if you really want to ensure that your sentences are correctly written as much as possible, since we are not native speakers, then there are tools that can help you with this. I don't know if you are acquainted with Grammarly. Grammarly is a tool. There is a free trial version. Where you put the paragraphs or sentences or even documents, and it marks where there are English problems, and sometimes in the free trial, not very often, but sometimes it proposes alternatives to your orthographical and grammatical problems. So try to use such kind of tool in order to write in English, because it's important that as much as possible you make sure that what you write is correctly written. So these are quality references that are important to consider, particularly in the moment of your education now, because you are going to go to the professional market. And this is important. This is a label of quality that you have to consider in order to sell yourselves as professionals. So that were my comments regarding the content and the way you answered. Yes, another and this is how do I say, a more an aspect about the way the hierarchy of the university works. One of the question was who was the advisor of the author of one of the papers that we read. Many of you identified the name of the advisor, but others got confused with the position of the author in Microsoft where he works. Okay, so in the university there is a hierarchy, and there are roles that professors can acquire depending on the mentoring that they provide to students. So normally, and if we use the English reference, there are lecturers and there are professors. At UTLAB, there is no such hierarchy, so everyone teaching you in your courses is a professor. Okay. So, and then when you have, I think that you do not do a final engineering project, but if you did, then you would have an advisor. An advisor is the person that follows the final project of some level of your education. So particularly when you do PhD, you have an advisor or several advisors, and which are the professors with people work with in order to obtain their PhD diploma. Okay, so what I was asking was who mentored, who advised the author, and well, it's Jeffrey Ullman, I'm sure that you know who he is. And okay, So that was something important to say because some of you got confused, and then well, and you can have also an advisor in master and an advisor in your undergraduate studies. So this is the name and the way the hierarchy in university is organized. Um, so these were the comments regarding the readings. Um, now, of course, that you decided to really copy paste sometimes the ideas that were given in the papers. Normally, what I would be expecting is that you summarize and synthesize what you read, and that you are able to produce your own way of explaining things. So in the future, please, if we do similar exercises, there is an effort to be done in order to really read, understand, be sure that you really get the message, and then write in your words what you understood. For example, there are questions like what does it do some, for example, how does approximate responses mean? Then you have to directly respond. Uh, the meaning of this concept is, and you give it. And even if in the article this is not given, of course all the elements that are given in the article should let you provide your own definition of some concept. Okay, so that's also an important thing to do at the level that you are. You should be able to exercise on this. Okay, we all struggle with this at any moment. So this is an effort that we have to do, but it's important that we do it because in that way we are sure that we make knowledge ours, and that we are, of course, able to provide our own critical opinion of the aspects of our education, our discipline. Okay, so this is things that I wanted to calibrate. Of course, here we will not have exams, and we will be like in a workshop, going back and forth on the material that you produce. But at the end, I will give a grade, and sometimes it's more dangerous to give these kind of grades because I will consider these elements in order to grade the whole work that you will produce in the course. So be aware of this. I'm asking for high quality production at all moments. Okay, do I have questions with respect to this? If there are no questions, and before, there will be a kind of parenthesis today and tomorrow. We will go back and forth on the example, practical example, and on the theory, real theory, where I speak for hours. Um, um, do not get confused about the type of work that we are going to do in the laboratory. In the laboratory, we'll really put hands into the matter and we'll go and see and analyze and understand in a very detailed manner the way tools, etc., work, and then we will produce some code, etc. Whereas here, it is more that, for example, we've been talking about NoSQL stores, and I have described the different families of stores. And now the idea will be to show you concretely how does such a store look like. Okay, and what does it mean to have a cluster, and how does it mean to put it in an external cloud, etc., so that you can really touch what I'm been blah blah bling during theory. Okay, so this is another perspective of the technical issues that might we might touch, okay? So in order, well, I am sure that you received from many different sites the announcement. In fact, in order to prepare the work to grade the first part of the semester, we are going to do 4 activities. Okay, so one of the activities will be getting acquainted with a key with a document store, see what is the principle adopted in order to populate a database and then to query it and then to manage it, because we will have a look at indexing problems and execution plans associated to the queries, so that you can really see in some of the internal, also the internal aspects of the way this works. And for that, we are going to use an example, MongoDB. And this is the sense of one of the announcements that I did in order to prepare these 2 sessions that we are going to drive in the week. So the first one is we are going to go through together, even if you have to prepare to have the cluster, Atlas cluster, etc., and so that you would prepare the environment. And then what will happen is that on top of that environment, we will do querying and as I said, other manipulations. And then we will have a look at particular storage problems. I have insisted a lot on the fact that the data cannot go to one server, so you need replication because you need to ensure certain properties, because you want also to make it possible to deal with the data in memory without and ensuring durability. And so we are going to see in MongoDB, it's a nice example because it exhibits how internally it shards the data, and then you can play with the shards and organize your data on the different shards. So we will have a look on this. This will be the 2 tasks that we will perform. And then we will do more or less the same on an example of a graph DB. And then there will be a use case. And the use case will be specification. You don't have to program. You will have to specify all the solution in a formal manner, so that eventually you give it to someone and that person can implement your solution. Okay, so that will be with all these 4 activities, we will have a grade for this first huge part of the data and cloud topics. Okay, the first step into these topics. Again, questions about this? Does everyone in my audience have managed to prepare the environment? Okay, and it was, I mean, you see that there are a lot of portals easy to use, so even if we are really doing some technical aspects, they are more or less easy. I mean, yeah, intuitively easy to use. Very good. Okay. And well, before we start, I'm not sure if today or tomorrow, but I will make some precisions in order to be ready tomorrow and start with the queries and with the sharding. Before I do that, I think that it's important so that you can really get the feeling and the what is behind the aspects of Mongo, I am sure that we have to consider some non-functional aspects before we really go to the example and see what's going on with Mongo. So I'm going to start sharing my screen and here. Right. So these are the slides that are available on the site. I'll continue with the same batch of slides. So until now, we have discussed a lot about the different of relational solutions and NoSQL solutions with respect to one evident property that changes, which is the data model. Okay, and you have seen, and what you have to bear in mind is that when it's normal when you change the data model, this has implications in the way you are going to manage your data on disk, and of course the interface that you will provide to the programmers in order to query your data. Okay, so you lose the relational model. This means that there is no there is no longer a query language. You can specify one, or you can adopt, as we have discussed, a more non-declarative approach in order to explore the data. And then once you do this, you can also decide to change the execution model. And this is another thing that NoSQL systems do, because that we discussed in the previous session, we are looking for performance. And the transactional execution model of the relational systems, the way it is implemented with all the properties, with the ACID properties, it creates, in some conditions, a certain overhead that NoSQL systems wanted to revisit. Okay, I'm not saying that transactions are not interesting. I'm not saying that they are not important. I'm just saying that for particular requirements, it is interesting to relax some of the properties in order to have a more agile way of managing the data. Okay? And so this group of properties, we are going to see which they are and how they have been revisited in NoSQL systems. First thing to bear in mind, the famous ACID properties of the transactional model adopted in relational databases. ACID are non-functional properties. Okay, what are well, this is in contrast to functional properties. Functional properties represent the application logic of a system. For example, if you are implementing an e-commerce system, your functional properties are all the operations that you provide in order to do e-shopping. Okay, I'm going to look for a product. I'm going to put a product in the chart. I'm going to do the addition, the summation of the products in the chart, and then I'm going to perform the payment, and I'm going to trigger the transaction, the purchase transaction, and trigger then the delivery of the transaction. So all these functions are the application logic, because the application is intended to provide all the operations necessary in order to do e-commerce. Okay? In the case of a data management system, all the functions are devoted to manage a database. So I can create a database, I can delete my database, I can update my database, I can, what else? I can read, look up, retrieve data from the database. Okay, this is all the functions that represent the functional properties of the database system. And then what is non-functional? These are all the properties that are important and that provide and that describe the guarantees that your system will give to users. If we come back to the e-commerce application, non-functional properties would be, for example, making sure that there is security in the transactions, particularly in payment. Okay, the payment will be done in a secure manner such that the data, the banking data, are not disseminated everywhere, and that no one will see this data in any way possible, and that the data could be hacked. Okay. Another non-functional property would be that if I have chosen a certain number of products that are already in my cart, if I do not go longer in my session towards, I don't know, 30 minutes or 1 hour, these products will be blocked in the catalog such that when I conclude um, my purchase, the system will not tell me that the products are no longer available. Okay, so they will be blocked, and when I finish, okay, and then if I take longer than an hour, then the products will be unblocked, and they cannot guarantee me that if I re-execute or if I want to pay, the products will be available for me forever. Okay, so these are non-functional properties. What are the non-functional properties in data management systems? Well, they are the ACID ones. It ensures atomicity, consistency, isolation, and durability. Okay, so these are the non-functional properties. And then I'm not sure that you know this, but when we go in a distributed setting, imagine that we have several DBMS working together in order to manage our data. Since there is the transactional model in all of them, if I have a set of different systems working and I want to ensure the same non-functional properties that each of them, I have to synchronize their local transactions. And there is a very famous protocol that makes it possible to design and to implement distributed transactions. And this is the famous commit phases, okay? And one that is very famous is the two-phase commit, okay? So the two-phase commit is intuitively very simple to consider. Imagine that we have two DBMS, one managing departments and the other managing employees. One is MySQL and the other is Postgres. Okay? So in the two-phase commit, and I want to update an employee, for example, I want to give the person a higher salary by changing this person from one department to another. Okay, so I'm going to change the salary of a person in Postgres, and I'm going to change the department in MySQL. So I do both operations in both systems, but all of them have to be integrated together, no, in order to have a global transaction. So the systems will execute or will open a transaction, they will execute the operation, and before the commit, they will inform each other that the operation has been done successfully. And if both of them, sorry, vote okay, then they will execute commit. Okay, so in that way, they will synchronize their transactions. And there is a famous model, any relational um, system provides this interface. It is called XAX Open. And with XAX Open, you get access to the different phases of the execution of a transaction, and you can implement two-phase commit. Okay, so and the thing is that, well, this you have guessed, this takes time, okay? Because I do not only have to take time in order that the transactions, local transactions work, but they have to come together to a conclusion. And since there is communication and since there is many processes, etc., so this can create overhead. And this is what NoSQL systems are looking for. How to relax these acid nice properties such that we can have a less overhead in the execution of the operations. And instead of having this acid, what they propose is a model called BASE, which is basic availability, soft state, and eventual consistency. So, which are the guarantees that now I can expect now from a system that normally when I retrieve my data, for example, from Atlas. Now that you have seen that when you created your Atlas cluster, there are three shards, three nodes associated to one of your projects. Okay, so you will have data distributed across these different shards, different nodes of your cluster, and basic availability says that whenever you ask for a document stored in the cluster, it will normally be available to your process. Okay, normally. Okay, not all the time, but almost all the time. And which would be at a moment in which you would not be have your data available. For example, if there is one of the node is isolated due to communication problems and you have the data there. Okay. Then we will see that with replication this will be overcome, but initially this would be the problem. Soft state means that particularly with regards to atomicity and to consistency, the system will accept that your process of the data goes through an inconsistent state. Okay. For some time, it accepts this, and then eventually all your data are consolidated and you have the same version across all the cluster of your data. Okay. So of course you have guessed, instead of having I do everything or nothing, or I roll back, I will accept in some cases not to have a certain level of consistency, and then once things have been synchronized, then I will consolidate the results. So first thing to keep in mind with non-functional properties and with regards to the execution model of NoSQL systems is that they adopt a base execution model. This is called also transactions. It's just another model of transactions. Now, another thing is, okay, so we are going to adopt this. And what are the properties on top of which this base model will be defined? In fact, there are three properties, non-functional properties, that will be systematically ensured at some point by any NoSQL system. The first, and well, they are organized in a triangle. I'm going to introduce the model in a moment. So you have available. Well, since we are going to refer to CAP, I'm going to start with C. Even if it is not strict, because we discussed, your colleague Mauricio asked about consistency, and we discussed that there are no integrity constraints, so there is no longer this strict control of consistency. And then you have duplication, and you have to consolidate the copies. So, but anyway, at some point you need your data to be consistent, otherwise it's a festival, no? So that's the first property. The second property is availability. So the idea is that even if we are not guaranteeing ACID properties, we are going to make sure that every time that some process calls for a document or a data item, the data will be available. And then the third one is fault tolerance partition. Fault tolerance partition means that you have a cluster, and the nodes are connected through a network. No? And then what happens if, for some communication reasons or because of some problem in the node, a node becomes available? This fault tolerance partition says that even if that node is not available, the system will continue working with the available nodes until the faulty node comes back to the cluster. Okay. So it will resist non-connection of certain nodes of the non-availability of certain nodes of the cluster anytime. Okay. So these are the three properties. Until now, are these properties clear for you? Okay, so, okay. And now,
Excuse me.
yes.
Sorry, could you repeat availability, please?
Availability? Yes, availability means that every time that a process asks for a data item, it will be available. Okay, even if it's in different clusters, even if one of the clusters, whatever happens, if you ask for something, you will have it.
Very well, thank you.
You're welcome. Okay. And now the question is, can I have everything? And you have guessed, in life we cannot have everything. So a very prominent person in the discipline came up in 2000 with a theorem called the CAP theory. Okay, so he reasoned about the possibility of a system of ensuring all these three properties, and he demonstrated that this is not possible. That if you want, either you can have availability and fault tolerance partition, but you have to sacrifice consistency. And if you prefer consistency and fault tolerance partition, then you will have to sacrifice availability, or availability and consistency, then you will have to sacrifice fault tolerance partition. Sacrifice doesn't mean that I will not have it at all, but that I will have it in a reduced manner, okay, depending on the protocols that I implement. So this is the principle of the CAP theorem, and this theorem makes it possible to classify the prominence of NoSQL systems that are in the nature. Okay, so when you choose a system, of course you will see what is the data model that it implements, and you will go and see which are the non-functional properties that it ensures and to which extent. And why? Because out of that, you will know which are the solutions that you as programmers have to program yourself if you want to increase the guarantees of your system, for example. And so if you are implementing a system on top of these NoSQL solutions, then and if you know that the system that you are going to choose ensures availability and consistency, so you will have to on your system, on your own system, will have to ensure protocols that will overcome fault tolerance partition if it comes up. And thereby you know how much time to market, how much engineering effort you will have to invest. That's if you in advance choose a specific solution. You can think the otherwise, no? You can think, I have an application that has a lot of A, B, and C requirements, and according to these expected requirements, I am going to choose a system that will provide me as much as possible the guarantees that my application is looking for, so that I can reduce my programming effort. Okay, I can concentrate on the application logic and not on horizontal properties that are very costly to implement. Fine? So if you are curious to really read what Eric Brewer is the author of the CAP theorem said, the seminal paper where he proposed this theorem is called Towards Robust Distributed Systems. It was published in one of the major conferences in databases, in POTS. And he also gave a keynote on that. So this reference is about his keynote, but there is the corresponding paper. Okay, so as promised, you have the CAP model, the CAP properties, and then we can see who is who in this triangle. Of course, I left here the data models reference, saying that this is the other aspect that characterizes the NoSQL systems, and I also kept in red the relational-based solutions, because the relational evolved, and there are today hybrids, very interesting ones that ensure and do interesting things out of the NoSQL spirit. Okay, so we have availability, which in practical terms, each client can always read and write. Okay, so there are no locks, so very relaxed locking. So you probably know about the two-phase locking protocol that is implemented in almost all relational solutions, that makes it possible to have concurrent reads and writes, ensuring that you will not have dirty reads. Okay, and so here it's the only thing that it says is that every time that a client, a process, will want to read or write an item, the process will be able to do it. Okay, the item will not be locked. And now you have a better answer to your question, to your previous question. This is what it means in reality, I mean, in practical terms. Now, consistency means that all clients always have the same view of the data at some point. Okay. Eventually, they will have the same view of the data. And then partition tolerance, the system works well despite physical network partitions. Now, there are systems that privilege consistency and partition tolerance, and they sacrifice availability, which are them, for example, MongoDB. Okay, so they use, what does it mean? That they provide a locking system in order to ensure concurrency, I mean, to get rid of concurrency problems. But this is how they ensure consistency, but and they resist partition tolerance. There are others. Big tables also very important. One HBase, both from Google. Um, Redis is also Google. Memcached is Memcached. That's a company, and Berkeley DB. It's a very popular one. We will see later on in our course. One of the most popular parallel models for dealing with parallel processing in big data was provided in the same project as Berkeley DB. And this is why it's also important. Then there are others that prefer consistency and availability, even if they are weak in partition tolerance. Of course, almost all evolutions of relational, okay, because consistency and availability are major properties of the ACID model. And then with partition tolerance, normally, even if they can work in a clusterized version, there is a master, so the cluster is hidden behind the master. Okay, so you never see the backend cuisine of the way the data is synchronized. You only have one entry on the system, and so even if they can have fault tolerance systems, you cannot see them. And another very important one, which comes out of the relational model, and this is important to notice because, again, when we will see these parallel models, an underlying way of having data feeding your parallel processes is having a relational solution provided by Vertica, for example. And then the other families are those that privilege availability and partition tolerance, and that have weak consistency models. For example, Dynamo that we discussed theoretically last time, Cassandra, CouchDB, the one that I told you that deals with versions of documents. These are very popular ones that have this preference. So as I said, when you will be decision makers at some point. So when you have to decide not only of NoSQL systems, now the historical moment is a little bit, it's not that separated, but if you are looking for a data management solution, the first guide is, of course, the data model, but the very important one, the one that will harm you because you are the ones that are going to program, okay? So the one that is very important for you as engineers is being aware of this triangle and trying to identify which are the properties that are provided by the system, okay? So a takeaway input of this part of the course for your professional life is exactly this. Okay, so you bear in mind the CAP triangle, and then you look for how to place the system that you are going to use, and now you can determine how much investment, programming and engineering investment you will have to develop if you are using this system for a given application. Or, as I said, in the opposite manner, you have a certain specification of requirements, and then what you will go and see is which corresponds best to the expected requirements, such that you reduce your engineering investment. Right? Everything simple and fine.
Doctor, may I ask a question?
Yes, of course.
Yes, I was just thinking in like now that we see like this like guide as you mentioned, and with respect to big data and data analysis, like I remember the paper we read like a week ago, I think. It talked a lot about querying and like modeling data and like giving data like a certain form. Like in that case, like if your project or your solution requires a lot of data analysis and big data manipulation, would it be optimal to use like I would think or I would guess that it would be optimal to use a SQL system or a relational database system because of the same querying problem, right? Because well, I'm not sure, but what I understood is that in NoSQL, like you don't have the same like facilities or simplicities as querying with SQL systems.
Yes, I understand your question. First, you have to think about the status in which you are going to work, the collection with which you are going to work. It depends the rawness status of your data. Okay, because if you have very raw data that you have to process, um, and the volume or the velocity is very important. If you choose any of these solutions, it will be very costly. Maybe the less costly will be the NoSQL solutions, but still you will have a very costly ETL process because you have to transform your raw data into the model that you choose, okay, or provided by the store that you choose. So that's a little bit of a problem that you have to consider. Now, relational data. Okay, so that's the first thing to consider, okay? Of course, if you compare the ETL challenges, of course, it will be less challenging to adopt a NoSQL solution rather than a relational solution because the transformation will be more challenging in the relational solution. You have to ensure a normalized schema. So you are starting from liter almost, and you have to transform liter into a pure and clean and consistent database. And you are not even sure that the input data is really consistent and clear and pure. Okay, so you might be able to exclude a lot of items that are dirty in order to really produce a relational database. Okay. So and with the NoSQL solution, this will be less costly, but if we are talking about huge volumes and velocity, this will be anyway very costly. There we will see later on that there are other lighter solutions that might be interesting if you are in this kind of problem. Now, with respect to what we read, the vision is very database vision, where queries the queries that are referred to are in a way relational queries or correlations, etc. But there are not analytic queries. Okay, so if we refer to the type of queries that the paper was considering, the most challenging thing was aggregations, okay, because all the statistical measures are aggregation measures in a relational solution. So let's think that you already have your data transformed, etc. Now what you want to do is to scale. Okay, so you want your queries to run very fast, despite that aggregations might be costly, computationally costly. So in that case, today the new version of NoSQLs are getting closer to relation, and there are more or less declarative solutions. There, the question is whether you are using a relational system that authorizes parallelization. If you are using a relational system that authorizes parallelization to perform aggregations, and that you require the ACID properties to deal with your data, then you would adopt a relational system because of you can delegate a lot of problems to the system, and this makes your life easier. Okay. Example of such kind of things, or everything that has to do with analytics, okay, aggregations like the cube, no, like the data warehousing, like requirements. If you have such requirements, then a relational solution would be interesting. If you have other types of requirements and that you do not care a lot about um, ACID guarantees, then maybe a NoSQL solution would be better. As I said, it depends also on the type of data. For example, if you have data coming from a social network, you have interest to use rather a graph database that will make graph operations easier to do. In the relational, it is possible to deal with graphs, but it works very bad. Scalability is poor in such kind of things. Okay, so this is why the tuning and the decision-making problems is hard to solve. Okay, and then the third thing that you have to consider is the organization in which you work. If you have an organization, a very strict organization, where managing and administration duties are related to very strict protocols. So you have to ask a supervisor and another supervisor whether you are allowed to do A, B, or C. Then you choose a relational. But if you have a very horizontal, you are working in a very horizontal organization in terms of hierarchy, then a NoSQL solution might be interesting because you have to have administration grants where you really can play with the system and you can add nodes, etc., in a very simple manner. So if you are in this type of organization, you would rather use a NoSQL solution. You
Okay.
asked me a very hard question.
Yeah. I think that was like what you just mentioned was actually my real question because like I think it's something that I really being like curious about. Like if I don't know if you start a company or you have a project, like what will you choose, either a NoSQL or SQL? But I think that with what you have said, I think it's clearer now.
Now, later on, we will see that in fact today people combine many solutions. So for some sectors of the data, they accept NoSQL, and then for others, they accept rather relational, and that's the way people are working today. Because, as you can see, there are a lot of variables to tune.
Yes, as you mentioned, like trade-offs, right? Like depending on what you
Yes,
want, or yeah, like your model, it's
yes,
the architecture you're gonna use. Well,
yes,
or philosophy and
yes, the architecture, and then the solution, the DBMS solution. Yes,
exactly. Thank you so much, Doctor.
you're welcome. Just let me see. Okay. And so the question was interesting also because now what do we choose and how do we compare? Okay. So once we have like in mind this cap, etc., then we can zoom in and consider how these properties are implemented. Okay, because for every property we have like 30 years or 40 years of people proposing protocols to implement them. Some less overheavy than others, so there's a profusion of solutions. Okay, And so we can, considering this, we can have a look at the different families and see how they manage to deal with all this. And if we want to compare um, the different families of systems, we can consider transversally to the CAP properties the following properties. Concurrency control. I'm sure that you remember from your operating systems course that concurrency control is very hard thing to implement. Okay, this is serious thing. And if now you imagine that you are in a distributed clustered setting, now it is really challenging. So you have interest to know whether the system that you are going to choose at least provides you with the different components that will facilitate the implementation of a concurrency control protocol. Okay, at least that, or if it really provides a solution. So first thing, you need concurrency control. Then, how is the data stored? I'm not sure that whether in the next reading exercise or the next one, the one that will talk, I think that's the next one with a paper of Michael Stonebreaker. When relational DBMS emerged, and I think that I told you that in the introduction part of the course, the hypotheses that were made towards the type of DBMS and the architecture, etc., that could be proposed was that the disk was displayed this with the arms going through the different sectors. Okay. So today, this is not the only technology, and this is why sometimes relational systems, I mean, at least the claim of Stonebreaker, who is not as some claim, it's a very important one, says, and the community is working in that way, that with new storage technology, some of the hypotheses must be revisited, okay? So you have to be aware of what is the hardware that that these systems can use in an optimized manner, okay? So anyone can use a disk, but the problem is that if you do not exploit it as in an optimum manner, your system will suffer. So the data storage that is supported, then as we have said, anyone at some point will need availability, and so availability is ensured since everyone is working on main memory. It's replication. So what are the strategies associated to replication, and then whether it provides certain transactions. So having a look at the different, for example, the first family, which is key value family, if you see, there is concurrency control ensured with two types of solutions, with locks, with two-phase locking, and with memcache, with a model known as MVCC. We will have a look later on the characteristics, because that's important that you know them. So the principle of MVCC, the locking solution works normally when you deal between hard disk and cache, okay? I think you have probably discussed this in fundamentals of DBMS. The relational DBMS works a lot with cache, okay, in order to ensure that your operations are done efficiently. So locks have to play with the disk and with the cache in order to ensure consistency and implement concurrency control. There are other ways based on timestamps, okay? And this MVCC plays with that, okay? So these are two, and of course, well, there's a lot of theory that we will not study here, but there is a lot of complexity theory analyzing the different algorithms implementing locking and implementing MVCC. And the way you decide what to use is with respect to the guarantees of the algorithms implementing this. Then with respect to RAM, to storage, key value systems, normally, well, the majority are based on RAM. Some of them play with hard disk. Others consider flash, and others even consider plugins that you can have in order to store your data. Replication is on some, this is more or less equilibrated. Some ensure asynchronous replication and others synchronous replication. Of course, synchronous replication has much more overhead because every node has to wait such that the data is replicated and then the operations are consolidated across the different nodes. And with asynchronous one, thanks to timestamps and other techniques, they will not wait until all the replica are consolidated in order to continue processing the data. And in the terms of transactions, you have some of them within a node, they deal with ACID transactions, okay? Or with at least some relaxed transactional model, and others not at all. Okay? So that's for key values, and then I'm not going to go into detail with this, but then depending on the family, you will have different solutions. And then, of course, here you have the relational and particularly the new SQL, which are evolutions of relational that adhere to some of the properties of NoSQL, where, of course, you deal with, you have the guarantees of ACID transactions, with some of them even accepting working with data in RAM, and of course with the guarantees of transactions on across all the cluster where the system is installed. Now, there is again a very interesting paper in 2011 that was again, there are three main database conferences, major conferences. Sigmod and POTS are an association, and then VLDB. So the paper here was published in Sigmod, and the title is Scalable SQL and NoSQL Data Store. So the question, since we, in fact, the ultimum objective is to scale. And why do we want to scale? Because in the backyard, we have big data lying there that needs to be processed in some way, okay, and managed in some way. So we need to scale. And on the upper part, that you have read in the paper, we have costly queries. Okay, so very costly workloads willing to process the data. And so in between, you have the DBMS that needs to scale in all possible manners. So how do we manage to do this? And so Rick Cattell discusses on what are the issues and how to manage to deal with this challenge. Of course, this was 2011. From 2011 to today, there are 11 years of difference. So now the arena is different, it has become a spectrum, and so things are not that clustered. But anyway, it's a good reference to understand how is the arena organized and why today we have all these different solutions. So what time is it? We're almost there. So I'm going to stop here just before this solution of multi-model databases. The multi-model databases is something that we are going to apply in the use case that we will go through by the end of this first term of the semester. So you will have time to think about different aspects. But before that, I believe that it is interesting that you go through a particular example. So for tomorrow, I just need to do a kind of survey. I know that I recommended Compass in order to, as a client, to interact with your clusters. Is this the case? Did you choose Compass as client for interacting with your? Yes. Okay. So I want to show you Compass. And did you manage to connect your atlas with Compass? It's just to know how. Yes. Okay. So this you are acquainted. You can do this, and then, well, at some point it will connect, because today I am having like little connection problems. Okay. So you are all connected. You have your atlas, and so in that way I will not go through examples by robot 3. Okay, that will be an easy way to. And did you manage to populate the database? I think you did, because it's I mean, it's just a button to. Okay. Okay. So we are ready for that. So tomorrow, when we will go through there will be an exercise where we are going to see an exercise of querying. Just today, I'm going to send by the end of the day a cheat sheet, so that you can have the reference of the different operations that you can do in Mongo, and particularly since I know that you are acquainted with SQL. So there's a nice cheat sheet where you have the expressions in relational and the correspondence in MongoDB, so that you do not get suddenly lost to do that. Okay, so the way we will work tomorrow is that, well, we will do some examples together, and then I will give you time after the course so that you can complete the exercise. Okay, so and the exercise will be graded with respect to mainly three different criteria. Of course, you have to complete the exercise. Of course, the results of the queries must be right, but this is almost obvious, because you will see the results in the system. So, and then for the indexing part, which is a more challenging thing, and the execution plans, there you will have to produce some conclusions about the observations that you will make, and in that way, this will be the first exercises. Okay, so tomorrow we will devote this exercise to that. I hesitate. Yes. I will also send another set of instructions, so that we can play with Docker for sharding. So just stay tuned to be sure that you will come already with this environment, so that we can easily use the hour and 15 minutes to do an intensive practical session. Okay, so that's what we will do. Okay, do I have questions before we wrap up?
I have a question, doctor, but it's regarding my personal status or a personal situation. So I know.
Okay, so maybe you can stay, okay, while
Yes.
the other
Sure.
leave, and then we can use the session to
Perfect.
discuss. Yeah. Other questions? I just think for those that were having technical problems, I responded on Slack directly to yourself. So have a look. And again, if I went, my email went to spam, go to your spam and see the results of the question. Nice day. See you tomorrow.
Thank you, doctor. Have a nice day.
Same to you.